Next up, we have Scott Aaronson. Scott Aaronson is David J. Bruton Centennial Professor of Computer Science at the University of Texas at Austin. He received his bachelor's from Cornell University and his PhD from UC Berkeley. Before coming to UT Austin, he spent 9 years as a professor in electrical engineering and computer science at MIT. Aaronson's research in theoretical computer science has focused mainly on the capabilities and limits of quantum computers. His first book, Quantum Computing Since Democritus, was published in 2013 by Cambridge University Press. He received the National Science Foundation's Alan T. Waterman Award, the United States PK's Award, and the Tomasoni Chisesi Prize in Physics. Please join me in welcoming Scott to the stage.
Hey, hi. Thank you so much for inviting me here. And so I'm excited to tell you about quantum computing in 20 minutes, or as much of it as I can. So in order to talk about quantum computing, the first thing we have to do is say a little bit about what is quantum mechanics. Now, don't be scared. Physicists for generations have, given people the impression that quantum mechanics is complicated and hard. I'm a computer scientist. I can let you in on a little secret, which is that it's not really as complicated as everyone makes it out to be, at least once you take the physics out of it, which is what we tend to do in the new field of quantum information. And so the way that we think about quantum mechanics is as a certain generalization of the rules of probability themselves. You can think of quantum mechanics as like an operating system that the rest of physics runs on as application programs. It's been the operating system for essentially all of physics for almost 100 years. Okay, and the core thing that it says is that we have to change the rules of probability. Okay, so everyone knows that quantum mechanics somehow involves randomness. Right, that this is what Einstein didn't like about it, that that God was playing dice. Okay, but if all that was going on was that events at the subatomic world happen randomly, that wouldn't be nearly so strange as the reality, right? What's strange is the rules that these probabilities obey, right? So what is a probability? It's a real number from 0 to 1. You could talk about the probability that your favorite team will win the Super Bowl, that it will rain tomorrow. Maybe it's 0.3, maybe it's 0.1. You would never talk about a negative half probability, though. That would just be nonsense. Far less would you talk about a probability that involved imaginary numbers. Okay, now, what quantum mechanics says is that to every possible way that a physical system could evolve, you have to assign a number called an amplitude. Okay, and amplitudes are related to probabilities, but they're not probabilities. They can, first of all, they can be positive or negative. They can even be complex numbers. Okay, and if I want to know how likely something is to happen, well, I need to know the amplitude for it to happen. And to know the amplitude, I have to add up the amplitudes for all of the different ways that it could have happened. Okay, now this is most famously illustrated with what's called the double-slit experiment. Richard Feynman used to say that sort of all of quantum physics is contained in this one experiment. It's where you shoot a photon, let's say, at a screen with two small slits in it. This picture is not to scale. And you look at where it ends up on a second screen. Okay, and what you find is that there were certain spots where the photon sort of never likes to appear, certain dark spots. And yet, if I were to close off one of the slits, then the photon can appear in those places. Okay, so to say that again, by decreasing the number of paths that a photon can take to get somewhere, I can increase the chance that it gets there. Okay, this is what doesn't make sense under the conventional rules of probability. The way that quantum mechanics explains it is that the photon has an amplitude for each path that it could take. So it might be that to get to a certain spot, it can get there by going through the top slit with a positive amplitude, or it could get there by going through the bottom slit with a negative amplitude. Okay, now if so, those two amplitudes are going to, as we say, interfere destructively and cancel each other out, so that the total amplitude will be zero and the photon will just never be seen there. Okay, now if I closed off one of the slits, then I make it so that the amplitude is only positive or only negative. Okay, and then the thing can happen. Okay, so this is what amplitudes can do that ordinary probabilities cannot. They can interfere, they can cancel each other out. So, to say it a little bit more carefully, the central rule of quantum mechanics is that if I've got any physical system, and if it could be in two perfectly distinguishable states, which, I'm a computer scientist, so let me call those states 0 and 1. And now I'm just going to follow the physicists in this notation that they use, these little angle brackets that denote quantum states. Then the system doesn't have to just be in 0 or in 1. It can also be in an intermediate state where it has some amplitude for being 0 and some other amplitude for being 1. Okay, we call that a superposition of the two states. Okay, and superposition, you can't really round it down to any familiar concept. It doesn't mean that the bit is either 0 or 1 and we just don't know which. It also doesn't mean that the bit is somehow 0 and 1 simultaneously, at least not in any simple way. Okay, if we look at a qubit, if we ask it, a superposition of a 0 state and a 1 state is what we call a quantum bit or a qubit. Hey, this is the basic building block of a quantum computer. Hey, now if I measure a qubit to sort of ask it whether it's 0 or 1, it will always pick one or the other. Okay, and it will, whichever one it picks, it will snap to that one. It will collapse to it, as we say, and it will pick 0 with probability that's the absolute value of squared of the amplitude for 0, and it will pick 1 with the squared absolute value of the amplitude for 1. Okay, and when you look, you just see a bit. You don't see a qubit. But if you don't look, if a qubit is kept perfectly isolated from the entire rest of the universe and from all other particles that could interfere with it, then it can evolve. These amplitudes evolve in time by different rules than the rules of conventional probability. This is how we know that nature works this way in the first place. In particular, we can do experiments where we see the amplitudes interfere with each other. Okay, now what's even more staggering and amazing is that if I had, let's say, 1,000 qubits, which could mean I have 1,000 particles, and each one has a state. Each one could be spinning clockwise or spinning counterclockwise, just to take one example, or it could be in a superposition of those two states. Okay, but now you might think that now I would have to give an amplitude, for each, 2 amplitudes for each particle, right? So each particle would have an amplitude for 0 and an amplitude for 1. And that would be 2,000 amplitudes in total. Okay, but that's not how it works at all. We need enormously more amplitudes than that. The rules of quantum mechanics are unequivocal that we need 2 to the 1,000 power amplitudes. Okay, that's 1 for every possible string of 1,000 bits. And that's actually more amplitudes than could be explicitly written down in the entire observable universe, which only has about 10 to the 85 subatomic particles. This is because, in general, the qubits could be correlated with each other. right? Measuring one qubit could tell us something about the states of the other qubits. The quantum mechanical version of correlation is what we call entanglement. Okay, so in general, if I have n qubits, let's say, then to keep track of what they are doing, I need a list of 2 to the n power complex numbers, okay, 2 to the n amplitudes. So, this is a staggering claim about the world. It's saying, just to keep track of 1,000 measly particles, nature somehow has to maintain, more information on some unobserved scratch paper, that we never see, than would fit in the whole observable universe. Okay, and yet we know it's there because it determines the probabilities of events that we can see. Okay, and anytime anything is done to those particles, those 2 to the 1,000 parameters get erased and replaced by new complex numbers, new parameters. Okay, now chemists and physicists have known this for a long time. They've known it mostly as a practical problem. You're trying to simulate quantum mechanics with a conventional computer. The difficulty of the simulation goes up, doubles at least with each new particle that you add. Okay, but it was only in the early 80s that a few physicists like Feynman and David Deutsch had the remarkable idea that if nature is giving us this computational lemon, why don't we make lemonade out of it? So why don't we build computers that themselves would be able to exploit, these same principles of superposition, of interference, entanglement, of an exponential number of amplitudes. Now, of course, they faced the question, well, supposing we built such a computer, what would it be good for? And they only really knew one answer to that question, which was it would be good for simulating quantum mechanics itself. Now, if and when quantum computing becomes truly practical, that's still the most important application that we know about. What really made people excited about this field was a discovery in the 1990s that quantum computers could do other things, problems having nothing to do with quantum mechanics. Much faster than classical computers are known to be able to solve them. Famous examples include breaking most of the cryptographic codes that currently protect the internet, solving machine learning and combinatorial search problems, somewhat faster than classical computers could. Okay, but now at this point, I'd better address maybe the central misconception about quantum computing that will arise in almost any popular article you'll ever read about the subject. And this is, people want to say, well, quantum computer is just like a conventional computer, except it gets to try every possible answer in parallel, and then somehow to sort of instantly pick the best one. Well, that sounds amazing. That sounds maybe even too good to be true. Okay, well, I'm here to tell you it is a little too good to be true. Okay, it doesn't quite work that way. Now, here's the problem. Okay, it's true that with a quantum computer, you can create a superposition over all of the possible answers to your problem. For example, all the possible keys to your cryptographic code, or all the possible settings of weights in your neural network. The trouble is, for a computer to be useful, at some point you've got to look at it. And if you just measured this superposition state, not having done anything else to it, then the rules of quantum mechanics tell you that all you'll see will be a completely random answer. And if you just wanted a completely random answer, well, you could have picked one yourself with a lot less trouble. Okay, so the only hope of getting a speed advantage with a quantum computer is to choreograph a pattern of interference among the amplitudes. So what you're trying to do is for each wrong answer, make some of the paths leading to it have positive amplitudes, let's say, and others have negative amplitudes, so that on the whole, they cancel each other out. Whereas for the right answer, you'd like all the paths leading to that to be pointing in the same direction, to be in phase with each other. So if you can arrange that, then when you look, you'll see the right answer with a good probability. Now, the tricky parts are you have to do this even though you yourself don't know in advance which answer is the right one, which would trivialize the whole thing. And you have to do it faster than anyone can figure out how to do the same thing using a conventional computer, right? Otherwise, what's the point? Okay, so nature is giving us this really bizarre hammer to use, this interference of amplitudes, and it's a minor miracle that there are any nails that hammer can hit. Anything that a quantum computer is good for outside the realm of quantum mechanics. Okay, so that's some of the theory. Now, there are a whole bunch of proposals for how you actually build a quantum computer, that are being pursued in parallel right now. You could, for your qubits, you could use the spin states of atomic nuclei, ions that are trapped in a magnetic field. Companies like IonQ and Honeywell are pursuing that. You could use cold atoms. You can use states of photons as your qubits. A startup company called PsiQuantum in Palo Alto is doing that. Microsoft is placing a very big bet on a very speculative approach called topological quantum computing, where you'd have to create a new state of matter that's never been seen before. Maybe the approach that's had the biggest successes so far has been superconducting qubits, where we build a chip. We cool the chip to about 1/100th of a degree above absolute zero. And at that low temperature, the currents on the chip superconduct. Superconductivity is a quantum phenomenon, and the currents can now be in superpositions of two different states. One can use something called Josephson junctions that go into this dilution refrigerator and that control, which qubit is doing which operation, or is interacting in what way with any of its neighboring qubits. Okay, this is an approach that has led to some spectacular successes in the last couple of years by groups at Google, at IBM, and other places around the world. Okay, now why is building a quantum computer so hard? Well, the central reason was understood since the 1990s. It's called decoherence. And it basically means unwanted interaction between the quantum computer and its environment, which has the effect of prematurely measuring the computer state, forcing it back down to being classical, right? I said before that this is what happens if you look, but crucially, it doesn't have to be you who's looking, okay? Any stray particle, stray radiation or air in the room that carries away information about whether a qubit is 0 or 1 will have the same effect on that qubit as if someone had measured it. Okay, so what this means is that if you want to build a useful quantum computer, then you have to keep your qubits incredibly well isolated from everything else in the environment. Okay, but they also have to be interacting with each other. Okay, and not only that, but in a precisely choreographed way. You have to be telling them what to do. Okay, so these engineering requirements are so enormous that there were distinguished physicists and computer scientists in the 90s who said, this will never be done. This is just impossible. Now, the key discovery that convinced most people that it was possible is called quantum fault tolerance, which basically says once you can get the error rates, the decoherence rates low enough, then you don't have to get them all the way to 0, because you can use sort of very, very clever quantum error correcting codes to get you the rest of the way. Now, unfortunately, we're not yet there. No one yet has a quantum computer that is good enough that you can use these error correcting codes to push the effective error rate down to 0. People are working on it. They are enormously closer to that goal than, let's say when I first joined this field, which was 20 years ago, okay? But they're not there yet. So what can we do in the meantime? So this brings me to the last thing I want to mention, which is Google just a year ago, astounded the world, I guess, with the announcement that they had, for the first time, used a programmable quantum computer, which they built in their lab in Santa Barbara, to achieve a milestone called quantum supremacy. Okay, now what does this mean? Quantum supremacy is a term that was coined by John Preskill, a physicist, 9 years ago, and it means using a quantum computer to do some benchmark task that we believe is hard for any existing classical computer. Okay, now notice I did not say a useful task. Okay, it could be completely useless. think of the Wright brothers airplane, right? It was not a useful airplane, for ferrying cargo or something, but it proved the point that, controllable heavier than air flight is possible. We want to do the same for quantum computing and actually beat all the classical supercomputers on Earth for some contrived task. Okay, now, it would be great to do that for a useful problem like factoring numbers, but that seems to require fault tolerance, which is maybe too hard. So, Google actually pursued a different approach for achieving quantum supremacy, one that emerged from theoretical work that I and others did about a decade ago. And what we proposed around 2011 was to look at sampling tasks. So these are problems that do not have a single right answer. There are an enormous number of possible right answers. The challenge is to sample a right answer with prescribed probabilities. Okay, so we suggested a way to do that called boson sampling that involved optics. So long story short, Google achieved quantum supremacy with 53 qubits with a different approach called random circuit sampling, still based on sampling. It looks like you'd need like 9 quadrillion steps to do the same sort of thing with a classical computer. And just a couple of months ago, a group in China actually implemented boson sampling and claims to have gotten quantum supremacy that way. Now, have they actually gotten it? Well, that depends on whether someone can beat the result with a classical computer. So, research continues, but it can now, I'm quite amazed. I did not expect quantum supremacy to be achieved by this point. And now, people can work on the next step, getting to actual error-corrected, scalable quantum computers, not just with 50 or 60 qubits, but with thousands or millions. Okay, thank you.